We're going to start talking about the law of conservation of motion, uh, and we're going to start by looking at a simulation of two objects uh, colliding with each other. You've got one object here that's moving to the right with a velocity of 1 meter per second. It's got a mass of 0.5 kilograms. Okay, that's shown right here. And you've got a second object, the green one, has a mass of 1.5. That's moving at negative 1 meter per second. So object 1 has a momentum of 0.5, and object 2 has a momentum of negative 1.5. So their combined momentum before the collision, the combined momentum is equal to negative 1. And we generally call that the initial momentum. So the initial momentum is equal to negative 1.00. That's the combination, the addition of both momentums. You've got 0.5 going to the right. You've got negative 1.5 going to the left. So you have a total initial momentum of negative 1 kilogram times meters per second. So let's run the simulation and see what happens to our momentum. And I'm just going to move the initial momentum over here. The initial momentum is moving over. And now let's run the simulation. They collide, and this is after the collision. Okay, they collide, and this is what happens. And we can see that the second object, the green object, has zero momentum. The reason it has zero momentum is it no longer has any velocity. So he's got zero momentum. And object 1 now has a negative momentum, and it's going in the opposite direction. Uh, and if you combine their momentums, you can see that our final momentum after the collision is equal to negative 1 plus 0. That's a negative 1. Negative 1 kilograms times meters per second. It's the same momentum before and after the collisions. And that's the law of conservation of momentum. The total amount of momentum is constant, or it's conserved, and it transfers itself through the collisions of objects. And a collision is contact between two or more objects. When two objects come in contact, it's considered a collision. It doesn't have to be, a giant crash between two things. That's is an example of a collision, but anything that interacts with something else, there's collision there. Uh, One of the things we want to take note of is notice that object 1 is now moving with a higher speed uh, in a different direction. And if we play that back, we can see that, before this guy had a velocity of 1. Now, after they collide, his velocity has gone in the opposite direction, and he increased the magnitude of his velocity. Is now 2. And the elasticity doesn't change this rule. What it changes is the elasticity changes the type of collision, which we'll get into it, but I'll prove to you that it doesn't change. So I'll make it less elastic of a collision, and we still have a negative 1 for our combined momentum before. If I run the simulation, the objects collide, Now they both are going this way, but it's still, the momentum is still conserved. Look, negative 0.52 and negative 0.48 makes negative 1. That was the initial momentum. Initial momentum equals final momentum. One way to write that would be, quite simply, initial momentum equals final momentum. And again, initial is before the collision, final is after a collision. Take some time to read the example problem that we're going to go over. It's basically a baseball being thrown into the catcher's mitt. If we, assume the catcher's hand is relaxed at the time of the collision, we can assume that there's no external forces. Uh, so we got to make a few assumptions here, but essentially the law of conservation of momentum is going to apply. Another way to think of this is put the catcher's mitt up and don't put somebody's hand in it. Throw the baseball into the mitt, and the baseball and mitt travel together after the collision. Okay, so a couple of things we want to note here is that the baseball is moving at 45 meters per second initially, and the catcher's mitt is originally at rest. So we can figure out the initial momentum and of the baseball and the catcher's mitt, and we're going to determine the post-collision velocity of the mitt and the ball. So afterwards, what's the mitt and the ball? So first things first, we know that initial momentum is going to be equal to final momentum, and we can expand on the initial momentum by calculating the initial momentum of the baseball and the initial momentum of uh, the mitt. So we just label these momentum of the ball initial plus the momentum of the mitt initial, and that's just making up the initial side of the momentum equation. And on the final side of things, we're going to figure out what the uh, momentum of the ball final and momentum of the mitt final is after the collision. So calculating this, we just need the mass of the ball times the initial velocity of the ball plus the mass of the mitt times the initial velocity of the mitt. And that's because momentum is equal to mass times velocity. Calculating 0.15 times 45, because that's the velocity of the ball, and 0.25 is the mass of the mitt, times 0, we get 0 for our momentum initial of the mitt, and our total momentum before is equal to 6.75. So that has to be equal to the total momentum of the ball and the mitt after the collision. So that initial momentum has to be equal to that initial momentum of 6.75 has to be equal to the final momentum. But we're after what that velocity is of the mitt and the ball after the collision. This may be hard to see, but what you need to understand about this type of collision is the fact that the ball and the mitt, after they collide, are traveling together now. They're both traveling off together. And you can envision this by one of two ways. You can, if you've played baseball before, it shouldn't be too hard to envision a ball being combined with a glove inside the glove, and they both move off together, and they're going to move off together at the same velocity. Uh, if you're having difficulty, we can go back to uh, our simulator, and I'll show you what it looks like when uh, two objects go off together at the same uh, together and combine to have the same velocity. Not sure where I left off, but I paused this somewhere around here, I believe. So we're seeing these two objects combine, and now they're combined and have the same exact velocity. The same velocity. Okay, you can see it here that they have the same velocity, and they're moving off together. They're combined, just like the mitt and the ball. And then uh, what we missed is we rewrite our expression. Let me back up here. We've got in here that the 6.75 equals the momentum of the ball final and the momentum of the mitt final. And, you know, this comes directly from this term, which comes directly from this term. Or excuse me, these terms come directly from this term. Uh, and if they're going off together, what we can say is that the final velocity of the ball is equal to the final velocity of the mitt. So you have two unknown variables here, which is what we're trying to find. Well, it turns out they're equal to each other. So instead of having two variables, let's just call these uh, one thing. Let's call them the final velocity because, you know, it's the same number. Uh, so we can call it the same unknown variable. So essentially we can replace that VF final for the ball with VF. The mass of the ball times VF plus the mass of the mitt times VF. So now we have one unknown variable. A popular way to rewrite this would be, you know, pull the VF outside of the equation, and you'd have mass of the ball plus mass of the mitt times whatever the final velocity is. So add those two masses up. Add those two masses up and divide both sides by whatever you get to solve for the final velocity. So the velocity of the mitt and the ball combined is going to be 16.9 meters per second. And if we want to put this in our simulator to prove that we're right, we have the initial velocity and momentum of ball 1, initial velocity and momentum of ball 2, they equal 6.75, which is what we got in our calculations. And if we allow this thing to run, and they collide and combine, you can see how their velocities change. You got the velocity of object 1 is now 16.88, and so is the velocity of 2, 16.88, which would round to 16.9, and that's what we got. And another thing that you can see in here is the momentum of both objects after, which we didn't calculate because the problem didn't ask us to, but if you add these two numbers up, or if you take that velocity and put it back into a momentum equation, you can figure out the momentum of both objects, of the ball and the mitt. Add those two up, you're going to get the same thing, 6.75, because the initial momentum has to equal the final momentum.